Generalized Pell's equation over algebraic number fields. The study of Pell's equation is an essential chapter in number theory, having roots that trace back to Diophantine analysis in ancient times. Classical Pell's equation, given by x squared minus dy squared equals 1, where d is a non-square positive integer, has been extensively explored in integer solutions. However, as number theory progressed into algebraic structures, the generalization of Pell's equation over algebraic number fields emerged as a fundamental problem with deep connections to quadratic fields, units in rings, and the arithmetic of algebraic integers. The generalized Pell's equation takes the form x squared minus dy squared equals n, where n is an integer, and x, y are elements of an algebraic number field. This documentary unfolds the remarkable journey of Pell's equation from its classical roots to its implications in algebraic number theory, discussing its solutions, theoretical advancements, and computational challenges. The origin of Pell's equation dates back to the works of Indian mathematicians such as Brahmagupta, who formulated a method known as Chakravala to find integer solutions. Later, the equation gained prominence through the works of Fermat and Lagrange, the latter proving that solutions always exist for non-square values of d when n equals 1. The equation was misattributed to John Pell by Euler, and the misnomer persisted despite Pell's limited contribution. The classical Pell's equation is deeply connected to continued fractions, where the fundamental solution can be determined through the periodic expansion of d. If the continued fraction representation of d is periodic, with a repeating sequence of length 2m, the solution to the equation is derived from the convergent of the fraction at index m. The minimal solution generates an infinite sequence of solutions via the powers of the fundamental unit epsilon equals x plus yd in the quadratic integer ring Zd. The transition from classical Pell's equation to its generalization over algebraic number fields was a natural progression, driven by the deeper understanding of quadratic and higher degree extensions. Algebraic number fields, which generalize the rational numbers by allowing roots of polynomials with rational coefficients, provide a richer setting to study Pell's equation. The equation x squared minus dy squared equals n in an algebraic number field now demands solutions where x and I are algebraic integers instead of rational integers. The fundamental unit in the ring of integers of a quadratic field plays a crucial role in determining solutions. In real quadratic fields, the unit group forms a cyclic group generated by a fundamental unit. If k equals qd is a quadratic field, the ring of integers is given by ok equals 0, where omega equals 1 plus d over 2 if d is congruent to 1 mod 4, and omega equals the square root of d otherwise. The solutions to the generalized Pell's equation correspond to the powers of fundamental units, extending the classical continued fraction approach into the algebraic setting. The central theme of solving Pell's equation in algebraic number fields revolves around the unit group of the ring of integers. In a quadratic field QD, the units form a multiplicative group isomorphic to z, generated by a fundamental unit epsilon. This fundamental unit is obtained through the continued fraction expansion of d, akin to the classical setting. Given the equation x squared minus dy squared equals 1, solutions in OK are structured as powers of epsilon, forming an infinite set of integer solutions. The generalized Pell equation x squared minus dy squared equals n requires additional considerations, as the presence of n not equal to 1 introduces complications. The primary issue is determining whether n is a norm in the field, that is, whether there exist algebraic integers x and y such that nx plus yd equals n. The solvability of such equations is tied to the structure of the class group and the existence of solutions modulo units. Beyond quadratic fields, Pell's equation extends naturally to higher degree number fields such as cubic and quartic fields. In these cases, the equation takes the form x squared minus dy squared equals n within the ring of integers of a number field K. The unit group in such fields is significantly more complex, often containing multiple generators instead of a single fundamental unit. For instance, in real cubic fields, the unit group follows Dirichlet's unit theorem, stating that the unit rank is given by R1 plus R2 minus 1, where R1 is the number of real embeddings and R2 is the number of complex pairs. This leads to systems of equations where finding fundamental units requires techniques beyond continued fractions, such as lattice-based methods and regulator calculations. One of the key challenges in generalizing Pell's equation to higher degree fields is the growth of the fundamental units. Unlike the quadratic case, where continued fractions provide a systematic approach, in cubic and quartic fields, units must often be computed numerically, using methods such as the LLL or Lenstra-Lenstra-Levaz algorithm for lattice reduction. The computational aspects of solving Pell's equation in algebraic number fields have become a major research area, especially with the rise of computational algebraic number theory. Algorithms such as Buchmann's algorithm for computing fundamental units in class groups, as well as Lenstra's algorithm for finding solutions to norm equations, play a crucial role in practical computations. In quadratic fields, the infrastructure of continued fractions allows for efficient computations, but for higher degree fields, the reliance on computational algebra systems, such as Parry GP, SageMath, and Magma, becomes essential. These tools implement sophisticated algorithms for unit computation, class group determination, and solving norm equations. Computational experiments have verified that Pell-like equations are solvable in most real quadratic fields. But general results for cubic and quartic fields remain open problems in algebraic number theory. The significance of Pell's equation in algebraic number fields extends beyond theoretical number theory into applied mathematics and cryptography. The solutions to Pell's equation in quadratic fields provide insight into quadratic Diophantine equations, elliptic curves, and class number problems. Furthermore, the equation appears in cryptographic protocols, where the difficulty of solving norm equations in certain number fields is leveraged for constructing secure encryption schemes. Another application arises in algebraic geometry, where Pell-like equations define certain algebraic curves whose rational points correspond to integral solutions. This connection to elliptic curves provides a bridge between classical number theory and modern algebraic geometry. The generalized Pell's equation over algebraic number fields represents a natural evolution of one of the most classical problems in number theory. From its origins in integer solutions to its deep connections with quadratic fields, class groups, and unit structures, the equation remains a cornerstone of Diophantine analysis. While the classical case is well understood through continued fractions, the generalization to higher degree fields presents formidable challenges, requiring computational techniques and theoretical advancements. As research continues, the interplay between Pell's equation and algebraic number theory will undoubtedly yield new insights, reinforcing its central role in mathematics.